All right. Full screen. Very ready to go.
Okay, good morning, everyone. I am super excited to be here. I'm Katy Wimberly. I'm an NSF NPS Ascend postdoc at UC Riverside. I work primarily with Laura Salas and all of my awesome collaborators listed here. I am super excited to talk to y'all about specifically Willman 1, an ultra-faint dwarf galaxy, and chemical abundances and the evolutionary history of our ultra-faints kind of in general. So this image, which was originally a video, I didn't do the proper PDF transformation, but this was created by Marcel Koski. It shows all of the Milky Way satellites. The green and red dots are all of the confirmed and candidate ultra-faint dwarf satellites. And in the video, as it kind of progresses through time of the discovery history of the Milky Way satellites, you see this big influx around 2005, 2010 of ultra-faint dwarfs because of Sloan Digital Sky Survey and other digital sky surveys like the Dark Energy Survey. We now know, have seen the tiniest and oldest galaxies we've ever seen in the universe. And because they're so tiny and so old, we really only see them around the Milky Way. So one thing that I love about this population of galaxies is that they can be used as a tool in cosmology. I know when most of us think of cosmology, we're thinking of all the awesome stuff that JWST is doing, but I like to use just our galactic neighbors through near-field cosmology. So because of awesome ground-based telescopes like Keck, we can really study in detail individual stars in the ultrafaint. And because all of the ultrafaints, we believe, actually stopped forming all of their stars during or because of the reionization epoch, they're really great kind of test beds to look at what happened in the early universe. So to really understand early universe physics, just doing it in our own backyard, galactic backyard. So my kind of go-to with ultrafaints is looking at their chemical abundances, and not just looking at their chemical abundances to try to figure out where the elements came from, where all the star stuff that we're made of came from, but to really focus in on, let's see if I can use the pointer, yeah, to focus in on the different star formation events that happened in the early universe to create these first stars, or these first galaxies and first stars. I in particular like to look at magnesium and calcium. So as you can tell, they're both formed primarily in supernova and dying high mass stars, but calcium in particular can also be formed in white dwarf supernova. So as we kind of get into the details of looking at these chemical abundances through different stars of different metallicities, we can really start to pinpoint the progenitor or the mass of the progenitors of these supernovas. So we get detailed information of not only the events that are going on in the early universe in these first galaxies, but different parameters of those first stars and first stars in these first galaxies. Now, one kind of big question with all ultrafaints is this an actual galaxy? Is it maybe a globular cluster? So in these two relationship plots from Josh Simon's review in 2019, you can see, especially here, that the ultrafaints really live at this interface between a globular cluster, or just like a population of stars, and an actual galaxy. Willman 1 is the star here, and it's really kind of living at this pivotal point where we actually don't have strong confirmation that Willman 1 is a galaxy. And even if it is a galaxy, we don't know yet if it's a stripped galaxy, if it's continually stripping as it's moving through, or if it's remnant. But it lives at this pivotal point where below that, if we really can confirm its status and learn more about this galaxy, we'll learn more about galaxy formation as a whole. And same when we're looking at the velocity dispersion across magnitude. There's these few kind of outlier galaxies here, and defining Willman 1 is really going to help us learn more about this distinction between globular clusters and galaxies. So that is the work I set out to do with Deimos in February and March of this year. So we looked at 9 candidate stars and 9 member stars and 8 candidate stars, and then kind of a slew of other associated stars here. Other than the kind of points I showed in the last slide, Willman 1 is pretty standard ultra-faint dwarf galaxy, which is nice because if it is a confirmed galaxy, then we can learn more about the whole population by studying this kind of common ultra-faint. So the first kind of order of business as I get into analyzing this data will be to really confirm its velocity. So this work here was done by Beth Willman in 2011. She's the namesake of this galaxy and published this really awesome work looking at 40 member stars and 5 kind of interlopers, or 4 interlopers, but 40 member star or candidate members of Willman 1. And as you can see, by looking at the line of sight velocity in different kind of distance projections, there's no real consensus of what even the systematic velocity is, or that it has any rotation within the galaxy. So using Deimos data, looking at getting this really high quality data will allow us to kind of say whether it's disrupting, whether it's an active galaxy. And that is exactly what we did. So we used the 1200B grading on Deimos, which is allowing us to push down further into the blue wavelengths and hopefully get some really awesome chemical abundance measurements. And if all 17 of these stars are actual members in the galaxy, then Willman 1 will automatically become the most chemically well-studied ultra-faint to date. And this kind of puts in context what we're talking about, like numbers wise, when we're looking at ultra-faint. Right now, Booties 1 is the most well-studied, and we have 13 member stars with 13 member stars that have chemical abundances. So even though these are all kind of small number of things here, we can really learn a lot because these chemical abundances are very, very detailed. So this is all very preliminary data. I used Pipit to reduce all of this. Pipit is amazing. Whoever is working on that, thank you so much. But I wanted to highlight here that when we're looking at chemical abundances, yes, we're looking at individual lines and individual stars, and it's all very detailed work, but it's really strong constraints, and these are really strong measurements. So with these, that 2 magnesium lines and 1 calcium line in just one of our stars, I'm showing that we can really, even just a quickly, sloppily fit Gaussian, get an equivalent width measurement for these lines. And there's not many like non-LTE effects that are going into these lines specifically. So there's a really strong constraint that we're getting on these very ancient stars to really deeply and focusedly learn about the chemistry in our early universe. So this is all work that I am starting now. I just wanted to kind of highlight my current work. So soon you'll see a work for me on chemical abundances in Hydrus 1. So Hydrus 1 is a ultra-faint dwarf galaxy that is also a satellite of the LMC and not just the Milky Way. And this is mainly seen in the south, so all of this data is from the Magellan telescope. But I'll use this kind of pipeline on Willman 1, so it'll be a really awesome, like, quick turnaround, I believe. And then with more Deimos data, I'll be looking at the mass metallicity relation in deeper detail with ultrafaint. And then because we know there's kind of some subpopulations in the ultrafaint, specifically those that came into the Milky Way system with the LMC, and we're starting to see chemical trends between the LMC satellites and the non-LMC satellites. Hydrus is an LMC, Willman is not LMC. So I can really get some detailed data there to show that maybe even in the early universe, there's some environmental dependence on what your star formation history looks like. And all of this work will kind of allow us to better pinpoint which of our ultrafaints are pristine relics of the first galaxies ever formed, so that we can have some targeted like sites to look for signatures for stars that were formed. And I'm a little quick on time, but I'm sure starting off ahead of schedule is good. So I will leave up my summary slides and am happy to take any questions.
All right, let's take some questions from the audience.
Sure. Two, and they're both naive, non-expert questions. One, just out of intellectual curiosity, what type of stars are you getting these metallicities at? Where do they live in there?
Right. Yeah, they're mostly red brown stars. We can do some like main sequence for now, but yeah, mostly.
Then a second question, if it's okay, on the science plot where things are classified as globular clusters or ultra faint dwarfs, what are the criteria that are used to make that decision?
Yes, so two primarily, one, is there a metallicity dispersion among stars? So we believe globulars are just a single population, no dispersion. So Willman 1 has a dispersion, but then we also use the velocity dispersion to show that the system is dark matter dominated to make it a galaxy, and we don't have that type restraint for Willman 1.
Yeah, what's the NV stand for on this chart?
Oh,
Sorry, can you repeat the question? We forgot to say that part.
oh, yes.
Yeah, thanks.
So the question is, what is the MV I guess just this figure, visual magnitude?
Were there any questions from the back?
No, not sure.
All right, yeah.
And one more, are you planning to determine whether it's a globular cluster or galaxy, and does that make a difference in your data as to if it becomes a globular cluster instead?
No, so actually, I think it'd be really interesting if it is just a globular, because we see that metallicity dispersion. So then it says something about, well, maybe our definitions between the two, but also like about globulars as a whole, if we want to stick to those definitions.
Great. Any other final questions? If not, let's thank Katy again.
Thank you.
So while the next speaker sets up, could we switch a little bit so that